Hi, my name is Evan Boland, and thank you for listening to Lab 4 for Physics 1, the Oscillation Lab. So for this lab, the objective was to examine the motion of a spring mass system in which the mass was swinging in an arc while oscillating upon a spring. Then, using tracker, we were to observe this motion and track the data points upon which it was oscillating, and then use a computational model to see what it would predict, and then see the difference between the actual data and the data that the computational model predicted. And finally, we looked at if this system satisfies the energy principle, ultimately finding out that it did. The reason why this lab is important is because not only are we able to predict complex systems such as this one, but also systems that would relate to this, such as if somebody were performing extreme sports like we saw in the introduction to this lab, it would be important to know those components that go into them so that we can make sure that they have safety restraints upon swinging on a very large rope swing or something of that sort. So the fundamental principles that go into this are also equally important, and they relate to all different types of systems throughout our world. And one of them is Newton's second law, which we've talked about multiple times over the course of this class. The fundamental principle states that the force is equal to the mass times acceleration of any given object, and we're going to use this to predict the actual final velocity of our spring as well as the position that it will take on. And it's going to be a derivation of this law, but it is going to be the same thing. And also the energy principle is extremely important, as we need to understand that the total energy is equal to the total work done in our system, and that total energy is equal to the kinetic energy, the gravitational potential energy, and the spring potential energy. And this obviously can be seen from this graphic right here. And another important thing to recognize is that our system just includes the mass block and the Earth is the surroundings. And this will help us to predict our different forces acting upon our object. So here is a graph that I found from the observations in Tracker. This is just a direct screenshot of it. But something that I need to point out before actually looking at the code is what we had to find from this data. And that would be the spring constant, the oscillation period, and the relaxed length. And these are all directly related to each other and directly related to this graph, as I had to find the oscillation based on the period starting at 0, and then the third actual lowest point again, divide that by 3 to find that my t was equal to 1.519 seconds. And then finding the spring constant from this, as you can see, was using the formula, the 4 pi squared times the mass of the object and divided by my oscillation period to find out that Ks was equal to 6.88 newtons per meter, and then finding the relaxed length based on the fact that the force of gravity is equal to the force of the spring. And then doing those calculations, I found that the relaxed length would be 0.127 meters. And then this is just a look at the actual code to the inside of GlowScript that I had to find in order to actually predict what the model would look like. And so this first box here is just our initial conditions, where put the mass in there and the initial position vectors, and the initial velocity was obviously 0, and then gravitational force had to plug in 9.8, my spring constant, and my relaxed length. And then editing these lines, as we can see, that is just directly related to the energy principle of what kinetic energy, gravitational potential energy, spring potential energy is, and then the total energy is equal to all of those added up. And then this next part of the code is actually what these different forces will actually be, and had to plug those in ultimately to find the graph to our right. And we're going to talk a little bit about how there is some error within here due to human error, but as you can tell, it should ultimately satisfy the energy principle, which on this slide, you can see a comparison between what the actual energy principle would be for a oscillating object upon a spring, and my graph, even though not perfect, does conserve energy. And the next thing we need to look at is the oscillations for y direction versus x direction, and they're a little bit different because the y direction was ultimately quicker, because it showed the actual oscillation of a spring, whereas the X direction also obviously included more of a pendulum type movement, and that is why its oscillation was 1.75 seconds and the Y direction was 1.519 seconds.